Okay, well, we're going to talk about 3.5 equations of parallel and perpendicular lines. So the first thing we need to review is what slope is. Slope is, we call m, and remember that's just rise over run, if you remember back from algebra. So for instance, if you had an xy axis, and say we have a line on that xy axis, doing something like this. Let's say we cross here at, we'll go 0, -2. Here we have a coordinate there, and then maybe up here we cross at, let's say, I don't know, 4, 3. Okay. Well, our slope then would be our rise. So how much we go up. So from this point here, and then our run. Okay. So rise and run at that right angle there. So it looks like we go from -2 all the way up to 3. So that gives me a rise of 5. And then a run, we go from 0 to 4, a run of 4. Okay. A rise and run of, in this case, 5/4. That would be our slope. All right. Now, if we have parallel lines, one thing that we know about parallel lines, and those aren't the best parallel lines, but I'm going to mark them as parallel using that our parallel line marking there. If lines are parallel, then we know that m is equal, okay, or they have the same slope. It's probably a better way to put it. They have the same slope if those lines are parallel, okay? And then recall from algebra perpendicular lines. Let's say so we have a line going like so, and then we have a second line cutting through that one perpendicular. We'll get our right angle marking there. Okay. Well, if this slope say was -2/3, this slope would have to be the inverse reciprocal. Okay. So this slope of this line would be 3/2. So slopes of perpendicular lines are inverse reciprocals of each other. It's just a fancy way of saying you change the sign and flip the fraction. So maybe give yourself an example. If the slope was 3/2, it would change from positive to negative, and then we'd flip that fraction over. It would become 2/3. Those are slopes of lines that are parallel or perpendicular. Okay, and here, if it was 2/3, it would stay 2/3 because those are the same slope. Okay, so now using that information, we're going to go ahead and use our slope formula to find the slope of a line containing -3/4 and 5/7. Okay, so this line has these 2 points on it. And we have to use our slope formula. So our slope formula, if you recall, is y2 minus y1 over x2 minus x1. Okay, and so what that really means is if I take and say, well, I'm going to use this formula, it really means you have 4 places where you're substituting in values. All right, and so if I call this x1, y1, and this one x2, y2, notice our 1's have to go together and our 2's have to go together. Our first x value and our first y value, our second x value and our second y value. We're just going to substitute those in. So we have y2 right over the top of x2. So 7/5. Okay, and then y1 right over the top of x1. So 4/-3. It's just a quick and easy way to put it into your equation there. In fact, my teacher that I work with, Mr. Vogel, uses that a lot, so it's a good strategy there. 7 minus 4 is 3, and then 5 minus -3, that becomes a plus, so 5 plus 3 is 8. So the slope of this line is 3/8. All right. Now, we're going to write the equation of a line that passes through a point and is parallel to another line. So in order to do that, we're going to use, I'm going to use point slope form. This is one way to write the equation. And so in order to get to point slope form, I'm going to use my slope equation that I have from up above there. And because when you have a numerator and a denominator, they're implied parentheses. And I'm going to manipulate that equation so that I get to point slope form. And so the way you do that is you would start by multiplying out the denominator. So if I multiply it by it on this side of the equation, it would cancel, and then whatever I do on one side, I'd have to do on the other. Okay. So for those of you like, huh? What's he talking about? I'm deriving this formula for you. I'm coming up with it. So okay, I'm going to go ahead and go x2 minus x1. I'm going to multiply by that here, and I'm going to multiply by it over here. Okay. I'm just showing you how we get this formula. Those two cancel, and I'm now left with m times x2 minus x1 is equal to, I'm left with y2 minus y1 on the other side. Okay, and really it's called point slope form because you're given one point and you're giving a slope. So we call it point slope form. So you're giving an x1, y1, and you're given m. So really the x2, y2, they're not going to be applicable in this equation because we're not given 2 points, we're only given 1. So I'm going to get rid of those 2 and leave the 1. So this is point slope form, if you recall from algebra. So what that means is if I know a point, which in this case I do, x1, y1, and in this problem I also can figure out the slope by rewriting this equation in slope-intercept form. So if I take and go ahead and move this 4x over to the other side, so subtract 4x here, subtract 4x here, I'm now left with y is equal to negative 4x minus 3. Well, the slope here then, m, is negative 4. So now I know a slope and a point. So I can write my equation, m times x minus x1 equals y minus y1. Well, m is negative 4. So plug in our negative 4, x minus, well, x1 is 1 equals y minus, well, y1 is negative 2. Doing some simplifying and getting rid of all these parentheses here, this would just distribute if we want it. Well, first, you know what, let me just write it without the parentheses. Negative 4x minus 1, so we have that one set of parentheses, and then y, two negatives make a plus. It would be perfectly fine to leave it like this. That is an acceptable format. Now, a lot of teachers or a lot of textbooks will want you to go to slope-intercept form, so if you did that, you'd have to distribute right here. You'd have to, in fact, let's do that up here. We'll say we have negative 4 times x minus 1 equals y plus 2. And so what I'd do is I'd distribute. So I get negative 4x plus 4 is equal to y plus 2. And then I get y by itself by subtracting the 2 over. So I get negative 4x. And then 4 minus that 2, when I bring it over, is 2, is equal to y. And then you just write it in slope-intercept form. You just move the y to the left-hand side. So it's y equals negative 4x plus 2. So either this format or this format would be perfectly acceptable. All right, so either or. All right. Let's see what else we got. Okay, let's write the equation of a line that passes through a point, this time and is perpendicular. So the previous one was parallel, so the slopes were the same. This one is perpendicular, so I'm given x1, y1. But now I need a perpendicular, meaning this slope is not going to be negative 4. The slope of my new line is going to be the opposite, which makes it positive, or the inverse, and it's a reciprocal. Well, the reciprocal of 4 is 1/4. Just flip it upside down. So 4 as a fraction is 4 over 1, and then that becomes not equal to, but it becomes 1/4. Okay, and it was negative, so we'd have positive. So our new slope is 1/4. So we take our slope or point slope form there. Let me fix that up. And you know what? I accidentally put that 2 in there. We don't have that 2 because we only have 1 point. All right. So that being said, our slope is 1/4. Our x and our x1, there we go, is -1 and equals y minus -2. Remember, these two negatives make a positive, so that's actually y plus 2. So you'd have 1/4 x minus 1 equals y plus 2. That would be perfectly acceptable, or if you wanted to change it to slope-intercept form, distribute that 1/4, so you get 1/4 x and 1/4 times -1, which is -1/4, equals y plus 2. And then move that 2 over, so you're going to have to subtract 2 from -1/4. That's going to give you 1/4 x minus 2 and 1/4 equals y, and then rewrite it. Y equals 1/4 x minus 2 and 1/4. I would probably just leave it in point slope form, but if you want to go to slope intercept form, that would be fine as well. Okay? All right. No, find the distance from, not form, that's supposed to read from. Fix that on your notes there, from, okay? Find the distance from 6, 3 to the line y equals -2x plus 5. Okay. So let me go ahead and graph. We shouldn't have to graph them, but I'm going to graph it to help us out here. We're going to go to 6, 3. Okay, so that is that point right there. And the line -2x plus 5, so we'll go 1, 2, 3, 4, 5. Go down 2 and over 1, down 2 and over 1, down 2 and over 1. And we get a line that looks something like that. Okay. All right. And now recall that the line, we want to go ahead and find a perpendicular distance there. All right. And so I can kind of guesstimate where that, I'll be like, it might be like right there, maybe. Okay. So that's kind of a guess. Now, that's not what we really want to do. Okay. We want to actually calculate it. So the first thing we're going to have to do is find a line that is perpendicular to our given line going through this point. So that's what we've been doing. So if it's going to be perpendicular, our new slope is going to be 1/2. So really our plan of attack, find the line perpendicular to our given line. Okay, and I'm going to separate these two problems so there's no confusion here. All right, so that's the first thing. So I'm going to use my point slope form again. So m times x minus x1 equals y minus y1. Okay, and so m is 1/2, so 1/2 times x minus 6 equals y minus 3. Okay, and I don't know why I put that extra parenthesis there, just habit, I guess. All right, so that means from here, I'm going to actually simplify this out and put it in slope-intercept form. So 1/2 x plus, minus 3 is equal to y minus 3. Notice I distributed. And then I'm going to add 3 to both sides. Well, now when I add 3 to -3, too many 3's on my mind, I wrote a 3 there. When I add 3 to -3, I end up with getting 0. So I just get 1/2 x equals y. This adding 3 here and adding 3 here makes them both cancel out. Okay, so my equation is y equals 1/2 x. So now I have two equations. I have this first equation, so I'm going to call that y1, and this is my second equation, y2. And what I need to do is find out where those two equations intersect. So if you think about this, recall that point of intersection, like if I was like, oh, just kind of sketching it in there. Yeah, that point of intersection is called a solution to a systems of equations. Okay, so the next thing you need to do, so like if this was the first thing, number one, number two, let's go ahead and switch up some colors here. The second thing you need to do is find where your lines intersect. So you're solving a system. Okay, and so my system that I have is y1 equals negative 2x plus 5, and y2 equals 1/2 x. Okay, well now if I look at this, if both, kind of ignore the 1 and 2 for a minute, and they both equal y. So if you recall from solving systems, you can use substitution or elimination or graphing. Well, graphing isn't working well for us right now, but I could use some substitution here. Okay, I'll show you how you could use graphing here in a minute. I'm kind of playing coy on that, but I'm going to go ahead and use substitution here. I'm going to plug that in for y, since they both equal y. Okay, I know that means that 1/2 x will equal negative 2x plus 5. All right, and if that's the case, if I move this 2x over by adding it, I'd have 2.5 x equals 5. And then if I divide by 2.5, how many 2.5s go into 5? Well, that would be 2. So x would equal 2. And if x equals 2, that's a key piece of info, because now I know that this, at least this point, is at the ordered pair 2 something. I need to find out what y is. Well, I can plug this x back in, substitute into one of these two equations, and find y. So maybe I put it into this bottom one. So y equals 1/2 of 2, which means y equals 1. So I get the ordered pair 2, 1. They intersect at 2, 1. Now, for those of you that were thinking ahead, you could hold on a second. I know the slope. Slope is 1/2. That means from this point, I'm rising 1, running 2 each time. So I'm going up 1 and over 2, and up 1 and over 2. Well, that means I'm also going down 1 and over 2 this way, or down 1 and over 2 this way. So hey, hold on a second. That's at 2, 1. You're right. That would have been a quicker way to do it, but I just wanted to be able to show substitution there. But graphically, if you have a graph, you could have done it that way as well. Okay, well, the last step is to use the distance formula to find the distance. Okay, that's what they asked us for, find the distance. So number 3, the last thing, and I'm going to have to squeeze it in over here on the graph, but number 3, use the distance formula. All right, so I'm going to write that right here. D is equal to the square root of y2, excuse me, yeah. Fix that up here for a minute. X2 minus x1 squared plus y2 minus y1 squared. So I'm finding the distance from this point to this point. Remember, it's my perpendicular distance. So I'm going from the ordered pair 6, 3 to the ordered pair 2, 1. So if I just label these, call this x1, y1, and x2, y2. Okay, so that would mean I'd have the square root of 6 minus 2 squared plus 3 minus 1 squared, which would give me the square root of 6 minus 2 is 4 squared is 16, plus 3 minus 1 is 2, squared is 4. Okay? Well, that equals the square root of 20, which, if we simplify, is is 2 root 5. That is the distance. Alrighty, that's quite the problem. Okay, gonna move on here. Alright, directed segments. Directed segments means you're moving from one point to another along a segment. And I'm going to call that, I'm going to think of my directed segment as a vector. Now, I talk about we a lot, but that's me and Mr. Vogel. Mr. Vogel and I, we thought about how to kind of work these problems out the best way and teach them. We really hadn't found a good way until this year. Mr. Vogel came up with a method that I think is going to be helpful. So, well, he said, let's think of a directed segment as a vector. Okay, and so we're going to think of this as a vector. For those of you who don't know what a vector is, it just shows magnitude and direction. And for that case, what we're going to do, if vector confuses you, we're just going to think of this as a line that has some slope to it. Okay, and I'm going to identify that slope right away. I'm going to go from A to B, and I'm going to say, well, that slope is 5 on my run and 4 on my rise. Okay, and I'm going to write that in a vector notation. So what I'm going to do is I'm going to take and write it like this using these types of brackets. So I'm going 5 on X and 4 on Y. And if I was going down 4, then I'd make it -4. If I was going to the left 5, I'd make that -5. But this is kind of like a vector notation, just showing the direction of the vector from 0, 0. Okay? All right. Let's find the coordinates of point R along the directed line segment AB so that the ratio of AR to BR is 3 to 2. It's quite the mouthful, but really what they're saying is where could you put point R along AB so that AR, let's pretend just for a second, R was right there. AR would be, you would have 3 pieces in comparison to 2 over here. Now obviously that's the wrong spot because these pieces would have to be the same. The other thing to think about is if we're going 3 to 2, that means you have a grand total of 5 pieces. Okay, so you think of that as like 3 plus 2. 3 plus 2 equals 5. So you're trying to figure out where to put that point R. That's what it's asking. All right, and so the way we're going to do that is we're going to think of it, well, there's 5 total pieces. And from AR, from A to R, that's going to be 3 out of the 5 of those pieces because it says AR to BR, and that's 3, 2, 5. So the AR goes first. And then we have the BR. The BR is going to be the 2 out of 5. So 3 out of 5 of those pieces is going to be AR. 2 out of 5 of those pieces is going to be the BR.
Please pay close attention to the next few calculations. You will find an error. See if you can catch it and correct it before I correct it.
Okay, and really you just set up your ratio here, 3/5. So I'm going to always start with my farthest left point. So in this case, A, like I'm reading the graph from left to right. And I'm going to take that 3/5 because it starts at point A and it goes to point R, and I'm going to multiply my vector by 3/5. So 3/5 of 5, well, that's 3 times 5 divided by 5, or 3. And 3/5 of 4, well, that's 3 times 4 is 12 divided by 5, or 12/5. For those of you who don't like fractions, this one actually terminates into a decimal. So if you feel better about it, you could call that 2.2. Or you could leave it as 12/5. For the sake of what we're doing, I'm going to call it 2.2. Okay? So we have the vector 3, 2.2. Now that is not the actual answer, but we're very close to it. So this says you're starting at point A and you're going to point R. How far are you moving? You're moving this far. So that means if at point A I'm at 0, 0, and I'm moving 3, 2.2, I'm just adding those two pieces up. That puts my new point at 3 and 2.2 in this case. Now, it's the exact same thing because we're adding it to 0, 0, but you won't always be adding to 0, 0. But note what that means. If I move over 1, 2, 3 and go up 2.2, that's right there. There's point R. And that means this length is 3 parts. This length is 2 parts. That's the 3 to 2. I think that's an ingenious way Mr. Vogel came up with there. All right. Let's try the next one. Find the coordinates of the point R along a directed line segment AB so that the ratio of AR to BR is 5 to 3. Okay. So once again, we're going AR to BR. And we're going 5 to 3. That means we have a grand total of 5 plus 3, or 8 this time. So that means we're going to have 5 8s and 3 8s. Okay? Well, looking at that, if we think of our slope, so from here, there, it looks like 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Okay? Our vector is going to be, and change in x is 8. Change in y is 6. And we want to go from A. So that's just going to be 5 8. And we'll distribute it. That's 5. 5 8 of 8 is 5. And 5 8 of 6, well, that's 5 times 6 divided by 8, or 38. Okay, and for those of you that are decent at reducing, 8 goes into 30. Grand total of 3 times with 6 left over. That's 3 and 6 eighths, or 3.75 there. Okay, so that might be the better way to think of it, 3.75. So let me rewrite that kind of nice and clean. That's 5, 3.75. Now, some of you just do it on your calculator and get 3.75. But note, this is the amount you're moving from A. Okay, so we've got to go back to point A, and point A is at, in this case, 1, 2, 3, 4, negative 4, and negative 1. And we're moving 5, 3.75. Which means we have to add those. So we get negative 4 and 5 is 1. And negative 1 and 3.75 is 2.75. My coordinate for point R is 1, 2.75. That is our coordinate. All right. So I really do think that that is the easiest method that I've seen to teach this. I've tried it a couple ways and it just has not worked well. And Mr. Vogel came up with that. I think that's great. Okay, so using vector notation there. Note that this is 5 8. It's A to R should be longer than B to R because A to R is 5 8, B to R is 3 8. This is 3 parts, this is 5 parts. All right, that's all we got there. Good lucky.